I'm the R&D sensor scientist at Palintest, Dr. James Jacobini. I'm joined by my colleague, Dr. Samantha Lunn, who's an innovation scientist, and we both work in the Sensor Technologies group here at Palintest. And today we're going to talk to you about understanding the science of the Kemio technology. So I just want to start talking about carbon, because carbon has actually found a lot of use. It's seemingly ubiquitous in electrochemistry of late as an electrode material. Some notable examples might include carbon nanotubes and graphene, which no doubt you will have heard if you've tuned into any technological sort of newspaper or article on perhaps the BBC. They're a real hot topic right now. Another one is boron doped diamond, perhaps a little bit less known, but no less important. And another one could be highly ordered pyrolytic graphite, which is essentially graphene but stacked in a much thicker sort of sample, but has similar properties. So the great things about carbon are that it has a high electrochemical activity. And what I mean by that is it's very conducive to oxidizing and reducing species at the electrode surface. It also has biocompatibility, because of course we're all made of carbon, so it has potential applications in biosensors and things like that. It's relatively inexpensive, and it has high chemical stability, which is very useful if you're going to put your sensors into particularly harsh environments or something that's maybe corrosive. You can be sure that your sensor is going to be okay. And screen printed carbon, which is what we use, really possesses many of these benefits, with the additional benefits that it can be manufactured inexpensively at a large scale. And you can see on the picture on the right there, this is a card that we manufacture here in-house via the screen printing process. And this card actually has 60 individual sensors printed onto it. These are then cut individually and packaged before use. So just if we look at one of these, a representation of one of these sensors up close. So I'll just go through the annotations on it, just so you're familiar with how it works. At the very top, we have the connection to the Cameo, which is the instrument that you use, and I'll go through that a little bit later on. That's essentially just where it fits into the instrument, and those are the electrical connections such that signals can get to and from the instrument. On the outer extremities, you have two working electrodes, 1 and 2. Now, the working electrode is essentially where we dose the chemical reagent, and that's actually where the electrochemical reaction happens and where the current may flow in or out of. Next, we have the counter electrode, which essentially completes the circuit. So, for instance, in a particular test, we may measure the current flowing between working electrode 1 and the counter electrode, or in another experiment with perhaps a different analyte, we will measure the current flowing between working electrode 2 and the counter electrode. And finally, we have the reference electrode, which does exactly what it says on the tin. It provides a stable reference voltage from which to measure from, because in electrochemistry, it's very important that you know what voltage you're applying to your system. So the picture you're seeing here is a very general representation. The geometries and sizes of those two outer electrodes could change depending on the sensor. And just to give you a more specific example of that, this is a sensor we make for the measurement of peracetic acid, which is a very useful disinfectant for all sorts of things. And I'll just walk you through briefly how it works sort of mechanistically. So if you look at the very top there with the arrows, so first of all, the peracetic acid, which I've abbreviated here as PAA, will react chemically with an iodide molecule. So that's the first step, which is a chemical reaction. And then that iodide molecule will become a triiodide molecule, which is another chemical reaction. And then finally, that triiodide molecule at the top is electrochemically reduced at the sensor surface. And that essentially means that electrons are flowing from the sensor into the molecule to convert it back into the I-. And that 2 electrons is what we measure as the current. So you can see there I've put out the chemical equations in case you're interested. But the interesting thing to know here is that this is the same chemistry as an ideometric titration. So we know it's very robust. Ultimately, all we're interested in is at the end, highlighted in red, is the current flowing through the electrode, which is proportional to the amount of analyte, which in this case is peracetic acid. Now, peracetic acid is a very useful molecule, but unfortunately, it's never present by itself. It's always in equilibrium with another molecule called hydrogen peroxide, which itself is a disinfectant, but not as effective. So hydrogen peroxide does actually react with iodide, but it reacts at a much slower rate. And because the test is complete within 1 minute, the time scale of the test means that any interference from hydrogen peroxide is negligible, and it really isn't a problem with this particular way of measuring it. So all chemical tests really may be susceptible to certain levels of contaminants. So this is another specific example of a sensor we sell, which is for the measurement of chlorine dioxide. And our sensors are specially designed to be tolerant to various contaminants in a typical water matrix you might find yourself in. So if you look at the table on the right, again, this is for our chlorine dioxide sensor. You can see there the typical contaminant and what sort of maximum concentration in milligrams per litre or parts per million you can withstand. So things like hardness or alkalinity, which you'd find in maybe tap water or something similar, it's tolerant up to 1,000 milligrams per litre. So you know that if you've got that sort of level in your water, with this sensor technology, you should be absolutely fine. So the eagle-eyed amongst you may have noticed in the peracetic acid slide in the chemical reactions that not only have we got the potassium iodide and the analyte, we've also got protons, which are hydrogen ions present in the reaction. And the pH really is just a measure of the concentration of those hydrogen ions. In fact, you'll know that if you've ever done a drop count test or a titration for instance, peracetic acid, you'll have had to add acid drops, and this is to control the pH. Now, Palintest sensors are actually fabricated with an onboard pH buffer, and this acts to control the pH in the surface, the volume close to the electrode surface. So this buffer is actually present at a very, very high concentration because it's dried onto the surface, which regulates the pH. Now, the upshot of that for a customer is that the addition of highly concentrated strong acid is not required. It's all built into the sensor. So just to sort of show you mechanistically how that would work is this molecule on the right is a typical buffer molecule. This particular one is phthalic acid. And the two important bits to look at are where the arrows are pointing to. There's two oxygen atoms there, and each one of those may either release a hydrogen ion or it may accept a hydrogen ion. Now, when we make these sensors, we tune the buffer such that the ratio of those two is very specific and it controls the pH in the surrounding solution. And simply by doing this, we're able to make sure that the pH is exactly where you want it to be, independent of the matrix, or rather the sample you're putting the sensor into. And this is very important for controlling reactions for things like peracetic acid or chlorine. So I've mentioned the sensors. I just want to go a bit through the Kemio device itself, actually. So the Cameo is a potentiostat specifically designed to work with our sensor technology, designed in-house by Palintest. It's portable, and it's easy to use, and it's very accurate. And just to emphasize the easy to use aspect, it has a built-in barcode scanner, and that allows easy upload of the batch information. So all a customer needs to do is scan that in, and all the hard work is done beforehand. It displays a clear on-screen result, which is saved on the instrument for later retrieval or analysis or anything you like. So I'll just go through that workflow that you can see in the bottom there. The first thing you would do is scan the sensor with barcode, and that just ensures you've got the correct sensor for the batch that's loaded onto the instrument. The instrument will warn you if it's a mismatch. You'll then fill your vessel with a sample, insert the sensor into the instrument and close the lid, and that's it really. The instrument will begin the measurement automatically, and within a minute's time you'll have your results. So it's very easy to use. And just to sort of show you what really happens behind the scenes, because it's always interesting to know, the Cameo primarily relies on the technique known as Chrono and Perometry, which is essentially just measuring the current as a function of time. And the way we do that is we apply a fixed potential to the electrodes. I mentioned earlier about having a reference electrode, which allows us to reference it to what we need it to be. And then we measure the resulting current over time. Now, I have a little animation on the right, which hopefully should show you how that works schematically. So the bottom pane there is the input signal, which is the voltage measured over time. And for this particular one, you can see we're using two different voltages over the course of 60 seconds. Now the upper pane in black is the resulting current. So that's the current that flows between the working electrode, either one, and the counter electrode. And we take this signal and we'll use it later on. So basically the higher that, or rather the larger the magnitude of that current, then the larger the concentration of the analyte. So this is a very simple, very robust technique. It's been used for many, many years. And a real key property of this is that the signal is electrical current, which is completely unaffected by color or turbidity. In fact, we've actually used this technique with customers in Canada. We're using maple syrup, which, as you can imagine, has got a pretty strong color and the technique was unaffected by this colour. So it's a real testament to how, as opposed to say photometry, how good Chrono and Pyrometry is compared to turbid solutions of things. I'm just going to pass over to my colleague, Dr. Samantha Lunn now, and she's going to take you through the rest of the talk.
Thanks, James. So yeah, I'm Dr. Samantha Lunn, and I'm going to talk to you about the sensor calibration. So I know that the title of this talk, and we've mentioned a few times that it's calibration free. The sensors are calibrated, but we do all that for you. So we do the hard part, so you don't have to. So when a batch of sensors is produced, we take a large sample of these and perform lots of tests on a series of known standards. So we titrate those standards, we know exactly what concentration they should be, and we test these at different temperatures. So in this instance, we know the concentration either in milligrams per litre or ppm, which is the same thing. We know the temperature either in degrees Celsius or degrees Fahrenheit. The only unknown here is the current which the sensor is going to produce. So we get all this data, retrieve the data from the instruments, and this looks something like this. So this is an example from a real batch from one of the calibrations that we performed on peracetic acid sensors just at 20 degrees. So we take a range of concentrations across the range of the sensor, perform this at many temperatures, gather lots of data to ensure that the sensors are accurate. This is all then fed into a 3D model, which is represented by the lovely rainbow plot on the left there. So you can see that for a given temperature or concentration, this relates back to current. So this is all captured in a QR code, which you then scan into the Cameo unit as shown in the picture on the right. So all of this rigorous data collection in the calibration is all incorporated into that barcode, and all the customer has to do is simply scan this, and all that information is loaded onto the Cameo. So after we've finished the calibration, we do a final quality check, an FQC check, where we run the instrument as a customer would, just to check that we're getting the correct accuracy in CV. So in this instance, we know the temperature, we know the current from the instrument, and then that data is fed back through the calibration to give you an on-screen concentration result. So the sensors only get shipped out of the customer once they're fully calibrated and have passed this final quality check to ensure that they are accurate and precise. So what does accuracy and precision actually mean? So accuracy is how close is the measured value, so the value you see on screen, how close is that to the actual value of the standard? So as an example, if we had a 200 milligram per litre or ppm solution, and the measured mean as produced by the Cameo was 194.2, this is an accuracy of 97.1%. Precision, this is about the variability of the repeat measurements and is often stated as the coefficient of variation, CV, or relative standard deviation, RSD. So in the table, there's some synthetic data which you could have a go at yourself in Excel or something like that. So this is just a typical representation of the range of values that would be expected for a CV of 4.8%. So if we look a bit closer at some of the test results, you can see that for test 1, we have a 210.1 milligram per litre, and for test 4, we have a 189.2 milligram per litre for a mean value of 197.8. So even though we have these values, they are well within the acceptable bounds of the test, so perfectly acceptable for this batch of sensors. So to look at that a bit more qualitatively, accuracy is how close the result is to the actual concentration, so as close to that bullseye on the dartboard as we can get, and the precision is the spread of data. So these can be completely independent of each other. You can have a very accurate but variable data set, which is represented in the bottom right, or you can have a very precise repeatable data set but not very accurate, which is shown in the top left. So we of course are aiming for the top right image, which is probed in our FQC tests to ensure that the sensors sent out to customers are very accurate and repeatable. So that's covered the sensor calibration, but what about the Cameo instrument? So the Cameo is sent out from the factory already calibrated, all set up and ready to go, but we do provide the Cameo with check standards, which are ran just exactly the same as a sensor test, but much quicker, so it's really easy, and it just gives you the peace of mind that the Cameo is performing as it should, and you'll see it pass on the screen and you know that the Cameo is performing correctly. And there's 4 different check standards, and this just covers the range of the instrument to ensure it's working at all levels. So once you've ran your sensor, your Cameo is all up and running, you can actually keep track of the results. So the Cameo offers a built-in tracking of all results, and this can either be reviewed on the device. You can go into the history of the device and see which tests have been performed, or you can download it to a computer to analyze in a spreadsheet, which is really good for data trend tracking or further analysis. Also saves the raw current data, which can be used for diagnostic purposes if needed. So in the table is just a typical example of the output of the Cameo. So you get a lot of information with the date, the time, concentration. You can input the user, the batch code. So that's all stored within the Cameo for good data management. That brings us to the end of the talk. And just to recap, we use a screen printed carbon electrode, which allows for the large scale and inexpensive sensor manufacture. We use these sensors with the Cameo, which primarily uses Chrono and Pyrometry to measure the analyte concentrations. Palintest does all the hard work for you, and we do a thorough calibration and FQC of each batch to ensure that all the sensors are accurate and precise. The check standards can be used periodically to check that the Cameo is working accurately and for long-term operation. And the Kemio makes data management very easy by tracking everything and allowing the download to the computer for analysis. Thank you very much for listening.